Okay. Good morning, madam. My name is Yan Karchai,
Tiêu Vân Khai.
Chu Mingwei.
and we are Group 18 from TC2L Lab class. Today, we will be introducing the topic of database systems and design. Let's begin with the basics. What is a database? A database is an organized collection of data that enables efficient storage, retrieval, and management that is crucial for digital systems. Metadata defines the structure and supports fast indexing and retrieval. The database management system, which is DBMS, software like MySQL, PostgreSQL, or SQLite lets users interact with the data. Procedures governs how data is used, ensuring accuracy, security, and proper querying. Altogether, the database supports reliable access, perseveres data integrity, enhances and access controls, and provides a foundation for scaling and discovering insights, even ontologies. Database can be classified based on several factors, including number of users, location, etc. Single-user databases supports one user at a time, while multiple databases allows multiple users to access data simultaneously, ranging from small workgroups databases to enterprise system spanning departments. In terms of location, centralized database store all data in one place. Distributed database spread across multiple sites, and cloud database offers scalable, accessible storage via cloud platforms. Applications environments vary too. General purpose database support diverse fields, while discipline-specific ones focus on particular areas. Usage-wise, operational database handle day-to-day transactions, and analytical database supports decision-making and historical data, warehouses, and OLAP tools. Finally, data can be structured, unstructured, or semi-structured like XML, which offers a balance between structured and flexibility. These classifications help organizations choose the right database system for their needs.
So the database design is essential because it forms the foundation for how data is stored, accessed, organized, and managed within a system. A well-designed database ensures efficient data handling, accurate information generation, and easier maintenance, while poor design can lead to data redundancy, data inconsistency, and difficult to track errors that can disrupt operation. It promotes data integrity through clearly defined rules and constraints, reduce anomaly, and support scalability as data needs grow over time. Proper design also improves overall system performance, clarify logical relationship between data entity, and enhance security by defining precise access control. Ultimately, good database design enable reliable decision making, pool user and organization productivity, and support the long-term success and integrity of digital system.
Next, database systems offer numerous advantages that make them essential for modern data management. They ensure data integrity and accuracy through rules and constraints, provide security by restricting access to sensitive information, and minimize redundancy by centralizing data storage. This not only enhances consistency but also improves information retrieval and sharing among users. Additionally, validation rules, access control, and standardized procedures help enforce organizational policies and maintain data quality. However, these systems also have drawbacks. They can be costly to implement and maintained, requiring advanced hardware, software licenses, and skilled personnel. The complexity may introduce performance overhead in smaller applications, and transitioning from older systems can be time-consuming and expensive. Despite these challenges, the benefits of database systems often outweigh the limitations, especially in environments that demand reliable, secure, and scalable data management. Having discussed the advantages and challenges of database systems, we now move on to practical part of this assignment, where we apply this concept through use of entity relationship diagrams (ERDs) to model real-world data structures and relationships. An ERD is a visual representation of data and the relationships between data entities in the system. It used primarily in database design to model how data is structured and how efficient how different data items relate to each other. There are three main components in the ERD, which is entities, attributes, and relationship connected by lines. Entities, which are represented by rectangles, is an object or concept about which you want to store information. A weak entity is an entity that must be defined by a foreign key relationship with another entity, as it cannot be uniquely identified by its own attributes alone. Attributes, which are represented by overs in Chen ERD or listed inside entity box in Crowdfoot notation. It is characteristics or properties that describe an entity and define what kind of data will be stored about each instance of that entity in the database. And last, relationships, which are represented by diamond shapes in Chen ERD or just lines in Crowdfoot's notation. It illustrates how entities are associated with one and another and are displayed using diamonds.
Okay. On the second question, we use a smart gene management system as the business plan for this part. This smart gene management system shows three basic types of relationship using simple chance and Crowdfoot model. First is the one-to-many relationship. One trader can manage many clients, but each client is only assigned to one trader. In the Chen model, this is shown with a hash connection where the trader side 1 is marked with a 1 at the and the client side with n. In the Crowdfoot model, it shows with a straight line on the trader side and a Crowdfoot on the client side. Next, in the many-to-many relationship, client can use many different devices and each device can be used by many clients. The change model shows with this with n or both sides of the word relationship, while the Crowdfoot model uses Crowdfoot on the both sides to show that it's go both way. Last, there's the one-to-one relationship. Each client gets one personalized fitness plan and each plan only belongs to one client. In both models, this is shown with a one or both sides or a straight line connecting the two entities. This model helps make it easier to understand how everything in the system connected in a clear and simple way.
For the last part, we created a business scenario based on a drop shipping company and designed a corresponding Crowdfoot ERD to reflect its structure. The business rules include the following. Customer must register before placing orders. Each order is linked to one customer and must contain at least one product, and each product is owned by one supplier. Orders can include multiple products, and each product within an order has a unique shipping status. Payment is made upfront by the customer, while suppliers are paid only after the returns window closes. Suppliers are required to maintain real-time stocks update, and customer can request returns within a specific time frame. Additionally, All products contain detailed information and may belong to multiple categories. All users and transaction action must be securely logged. Our ERD captures all essential components, entities, attributes, primarily and foreign keys to maintain data relationship and various relationships such as one-to-many and many-to-many clearly defined with participation, constraint, and cardinalities. In conclusion, this project allows us to gain a comprehensive understanding to both the theoretical and applied aspects of database system. We learn to represent real-world entities and relationships through ER diagrams, understand the significance of normalization and constraint, and appreciate how databases supports data integrity, security, and efficiency. Overall, this experience strengthened our skills in analyzing and designing robust database system suitable for dynamic business needs. That is all. Thank you.